Okay, let's start at the E603 linear system theory. Today we will introduce something about the system properties. The first title for this class is Introduction to System Properties. Here we list the model for systems. Basically we have input, we have output. The link the input to output we call the system. Or we can think about the system is the one to make the signal input change to the signal output. We will use many different terms to describe the systems, like a linear system, or time invariant, or memoryless, or causal, or stable, or something else. So during this class, okay, we will use some default notations. When we say X, that means we are using input. When we say Y, we're talking about the output. When we talk about the system, we're using H. Okay. Let's first think about what's the linear system. Let's consider a soda machine in real life, because a soda machine is a real concrete system. For this system, the input is the cash you put in, the output is the soda pops out. So soda machine basically is a linear system. Why? Because from the definition of linearity of system is, if you put $1 in, you get 1 Coke, you get $2 in, you get 2 Cokes out. So if you pop up to N dollars in, you get N Cokes pop up. So that means if you linearly change the input, you will get the same amount of output change. So that's the idea about the linear system. Furthermore, let's think about the vending machine, which can provide both Coke and coffee. Let's say $1, you can buy 1 Coke. You get $2, you can buy 1 coffee. If you need 3 Cokes and 4 coffee, so basically you just use 3 multiplied with 1 Coke and plus 4 multiplied with 1 coffee. That's the total you have to pay. So the basic idea about the linear system is, first, if you put $2 in, you get 2 Cokes out. But if you put the $2 separate, let's say you put $1, you put another $1, actually the output should be exactly the same as you put the $2 at the same time. Okay. Another idea behind it is, let's imagine if you go to any supermarket, if you buy a lot of food, okay, you can buy some Coke, you buy some fruit, you buy some bread, you buy some eggs, you want to pay. When you go to the cashier, okay, the cashier will never give you one single price, okay. But the cashier will say like this, let's do one by one. He will first check your bread, how much you need to pay for your bread, how much you need to pay your eggs, how much you need to pay for your soda. So finally, just add the price together, that's the total you need to pay. So basically this is the linear system. The linear system tells you if you have a very complicated input, you can always decompose the input to many small pieces. To make every individual small pieces is easier to handle. For every small input, you get a small output. Every small output, when you add them together, that's the total output you need to pay. So that's the general idea about the linear system. So mathematically, you can think about it this way. If you have x1, you have x2, they both get some output y1 and y2. If you take any linear combination of ax1 plus bx2, accordingly you should get ay1 plus by2. So if we treat here x1 as $1, y1 as 1 Coke, that's exactly what we talk about in linear system, right? If we treat x2 as $2 and y2 as 1 coffee, then the above formula just specify the same thing in the previous vending machine example, right? Let's think about what's the time invariant system. So basically, if you look at the term time invariant system, it talks about the system response never changes over time because the time invariant, right? Nothing changes over time. Actually, soda machine is a time invariant system because soda machine is always a soda machine no matter when you want to use it, right? whenever you want to use it, $1 always get one Coke. Okay, you put $1 in the morning, you get one Coke in the morning. You get $1 in the late evening, you get one Coke in the late evening. So the input shift a little bit over time, the output will also shift a little bit. Let's think about it. In the real life, let's say there's a restaurant in Hoboken, okay? It provides some lunch special, okay, for a sushi box from the 11:30 to the 4 p.m. So after 4 p.m., the same sushi box is raised to $11. So is this a time invariant system? But that's obvious, right? Because the same amount of money, you cannot buy the same amount of food at different time slots, right? So that's the time invariant system. For the time invariant system means whenever you put the same amount of input, you should get the exactly same amount of output. So the system always has no discriminative treatment about your time slots. Let's think about what's a time invariant system by definition, okay? It's very simple. If you have xt, you get output yt. If you shift the input xt with t naught, your output yt also shift the same amount to y to t minus t naught. For example, this function, this is time invariant, but this one is time invariant. So in the following discussion, we will explain why, okay? Let's think about what's the causal system. If you think about the causal system, let me ask you this way. Can I ask the soda machine, say, hey, please pop up a Coke for me? I want the Coke today, but I promise to input $1 tomorrow. No, usually that's no way, right? Because the soda machine is a causal system. The causal system means I only care about how much you put now. I don't care about what you put in the future. Okay? So because the output can never happen before the input for a causal system. That causal system is very consistent to our common sense in real life, right? Mathematically, you can think about it this way. If you have a function like this, that means the output is accumulated integration of the input from negative infinity to t. Okay, that only integrates all the input till current time, no futures. But this one is a totally different story, because this one integrates all input past current t and future t plus 1. Similarly, for this discrete time causal system, you see, this output yn only accumulates the input till the current time n. But this one, if you look at the yn here, you have two inputs. One is n plus 1, one is n minus 1. Okay? But the content of the current time n, xn plus 1 is always future, right? It's always future input. So that's the non-causal system. The next one we talk about the memory system. The memory system means the system output only depends on the current input, neither the past nor the future. The same thing if you ask the soda machine will be typical memory system. You can never say, hey, please pop up a Coke for me today. I promise to input $1 tomorrow. No, because the soda machine can never trust you in the future. You can never say like this, please pop up a Coke for me today. Can you recall that I paid you a lot yesterday? No, because the soda machine has no memory. It doesn't care about what you did yesterday. So the soda machine only care about right now how much you put. Doesn't matter how much you will pay tomorrow. Doesn't matter how much you paid yesterday. No promise in the future, no credit in the past. Only current input works for the current memory. So that's what we call the memory system. So mathematically, you can think about it this way. For this formula, this output only depends on input xt at the current time. So nothing else. So that's the typical memory system. But for this function, You can say the output is integration over all different inputs from the negative infinity to current t. So you need a memory to remember what happens before. And similarly here, that's the memory system. The y only depends on current input x. This one, you have some future input, you have past input. So that's the typical memory system. The last one we talk about the stable system. The stable system means the system output cannot be infinite if the input is finite. Just imagine you put $1. $1 is $1. It's a finite input. You put $1 in, if the soda machine pop up soda's endless forever, what you can say? The soda machine must be crazy, right? Because crazy here means the soda machine is not stable. It only has one destination, either dead or exploded. A similar situation here, if you have a system, you want to make this system stable, you have to make sure the output can never achieve infinity. Just like you drive any car, you have some gasoline as the input. You can use the gas, you press the engine, you get high speed, but you can never expect the high speed to go to infinity. If the speed goes to infinity, what happens? The only destination is explode your car. So mathematically, you can think about this way. If you put some finite input, hopefully the output also be finite. Okay, that's the people call the bounded input with the bounded output, or can think about this is the BIBO. Many people, get frustrated. How to prove this system is a stable system? Actually, there's a shortcut. You just replace input. You just pretend that the input is a constant. If the input is a constant, the output should be bounded. Or you think about it, the output should be less than infinity. If that's true, that's the stable system. Otherwise, this is non-stable. For example, that's the output yt equals txt plus 3. So if I assume xt, the input is a constant, so you take absolute value of the output, you will find what? That approaches infinity. Why? Because this xt is c, but the t can be as large as you can, right? If t is infinity, the output is also infinity. So this is the non-stable system. Let's look at the stable system here. If we assume xt, the input is a constant c, so the shift version is also constant, right? It's also c. The shift xt plus 1 is also constant c. So the output yt take absolute value should be less than c take absolute value plus c squared for whatever t. So the output is bounded. So this is a stable system. So we have similar situation for discrete time examples. Now let's take two specific examples to demonstrate how to mathematically to prove the system with different properties. The first one is think about the linear. When I say this function yt equals xt minus 2 plus x2 minus t, I can say definitely this is linear. Why? Because the output contains two copies of the input, xt. Also with some time shifting or flipping, I don't care. Because the linear system only care about if we change the input magnitude, how the magnitude of the output changes. They don't care about the shifting over time. For example, let's think about if xt is doubled, right? The shift xt minus 2 also doubled. The x2 minus t, the flipped and shift version also doubled, right? This component doubled, this component doubled. Of course, the output also doubled, right? So on and so forth. If this is tripled, this is also tripled. The output also tripled. So definitely this is linear. Mathematically, we need to do something like this. We need to assume we have two given inputs, x1 and x2. They generate two separate outputs, y1 and y2. Now for a new input, this is the linear combination of the two inputs, x1 and x2. X equals ax1 plus bx2. We should have a new output y. This y from the system, you see that should be xt minus 2 plus x2 minus t. Now what's xt minus 2? Based on here, right? Xt equals this. So xt minus 2 should equals xt should equals ax1 t minus 2 plus bx2 t minus 2. You just replace t as t minus 2 here. You just replace t as 2 minus t, you get this one. We plug in these two terms to yt, make some necessary arrangement. You see, yt basically equals a times y1 plus b times y2. So the meaning is here, you have input is a linear combination ax1 plus bx2. The output also equals ay1 plus by2. So the linear combined inputs end with the same linear combined outputs. So this is the linear. Let's think about what's the time invariant. Intuitively, we can think about this definitely is a time invariant. Why? Because look at this term, you have a negative sign in front of t. So the meaning here is, so any time shifting here with t will be flipped with the opposite directions. Remember, for time invariant system, what do you mean? You shift a little bit with input x, you should have the same amount of shift with y. But unfortunately, for this term, if you shift a little bit with input, the output will have some opposite shift. So this is not a time invariant. Of course, mathematically, we need to prove in this way. You have two input x1, x2, you get two output y1, y2. So we need to assume the second input is a shift version of the first input. Or we can say x2 equals x1 t minus t naught. You have some shifting here. So let's look at the y2t. That contains x2 t minus 2 and x2 2 minus t. So for this first term, this should be equals x1 t minus 2 minus t naught. Why? Because you can just replace t by t minus 2, right? You got this term. Similarly, x2 2 minus t, you just treat 2 minus t is a whole thing, so that should equals x1 2 minus t naught. So we plug into y2t, you get something like this. And meanwhile, let's examine what's the shift output y1t minus t naught. y1t minus t naught means every t in this function is replaced by t minus t naught. So that's the term for y1t minus t naught. We need to compare with y2 and y1t minus t naught here. If they are the same, then this is a time invariant system. Otherwise, we call it time invariant system. But actually, when you compare with, the problem is coming from the second term. You see, you have plus t naught, but here you have minus t naught. Because the output y2 is not a shift version of the y1, so the shift input doesn't result in the same amount of shifting with the output. So this is not time invariant. We call it time invariant. How about the causal? Let's look at causal here. Because for this yt, this contains x2 minus 2, x2 minus t. These two terms have two opposite shifting directions. So that means if one of them is the past, the other one must be the future. But we know if you have some future input for the output, then this must be non-causal. Mathematically, you can very simple, just use one special case. You put t equals 0, see what happens. If t equals 0, the output of yt equals y0. y0 equals x minus 2 plus x2. Look at here. What's x2? At the timestamp t equals 0, x minus 2 is the past input, while x2 is the future input. Therefore, this is the non-causal system. Here, let me remind you, you can use the special case to prove this is the non-causal, but you cannot use this way to prove this is the causal system. Just like if you really want to, let's say you want to say this guy is honest or not honest. If you want to say it's not honest, it's simple. You just list one example, right? Let's say he lied yesterday. Okay, then we say this guy is not honest. But if you really want to prove this guy is honest, you have to say in all the history he's always honest. You cannot just take one day to make this judgment. So the same thing for this causal judgment. How about the stable? That's also simple, right? As I mentioned here. Because Y only consists of two copies of the input. Even you have some time flipping or shifting, doesn't matter. Because we only care about the magnitude for stable systems. Because you only have two copies, if xt is bounded, of course the yt also bounded. So this is the stable system. Mathematically, we can use something like this. Let's assume the input xt is constant c. So what's the absolute value of yt? That's very simple. It's 2 times c. Take the absolute value. You see, you have a bounded input. The output is also bounded. So this is the stable system. How about the memories? For this memory system, actually, that's also very simple. Because look at this. You have 2 shift copies of the input, right? So it must be the memory system. Because when you have some time shifting, you need extra memory to remember what happens. For memory system, you only have the carried input. You can never shift any input. There's also another explanation here. Recall that in the previous discussion, we know this is the non-causal system, right? What's a non-causal? Non-causal means you have some future input in the output. When you have a future input, what does it mean? You need a memory to remember what happens in the future, right? So definitely this is the memory system. Generalized, we have 2 statements here, okay? One, you can say, if you have a non-causal system, this must be memory system. Because non-causal means you need a future. Future means you need to remember what happens in the future. If you have memory system, what does it mean? Memory system means nothing future, nothing past, only current. If you only have current, you have no future, of course this must be causal system. Let's switch to some discrete time systems. Is this linear? Of course, because this Y only contains 1 copy of the input. If the input scales something, the output also scales something. So that's the very intuitive. This should be the linear system. Again, linear system only care about the magnitude, doesn't care about the time shifting, time flipping, time scanning. So mathematically, you can think about it this way. You have 2 input x1, x2, you get 2 output y1, y2. Now you get a new input is a linear combination of the 2 inputs x1 and x2. Like this, you get a new output yn equals x2n. Let's replace n with 2n. Then you get x2n equals a x1 2n plus b x2 2n, right? Because this formula, right? From this formula to this formula, just replace n as 2n. So x2n is yn, right? So yn equals to x2n equals a y1 plus b y2. So the linear combined input get the same linear combined output. This is the linear system. How about the time invariant? Intuitively, I can say no. Why? Because you have the scaling factor 2 here. If the input shift a little bit, the output will be what? 2 times shift. You need double shifting. So that's the time invariant system. Mathematically, if you really want to prove it, you can say we have 2 inputs, x1 and x2. Each end with the output y1 and y2. Let's assume the second input x2 is the shift version of the x1. Then the output should be equal to something like this, right? y2 equals x2 2n and equals x1 2n minus k. because this exactly followed here, right? X2 and X1 is a shifting version. And meanwhile, let's think about the time shifting output Y1 n minus k. So for this formula, you need to replace every n by n minus k. So you end with y1 n minus k equals x1 2 times n minus k. So let's compare with the shifted output and this the output with the shifted input. They are not the same. So this is the time invariant system. How about the causal here? No, this is not causal. The reason is you have 2 times of n for the input. So that means the input has been squeezed over time index line. If n greater than 0, the output always depends on future inputs. Mathematically, you can also choose one special case. Let's say n equals 1. You have y1 as output, but the input is x2. For the time 1, x2 is future because 2 is greater than 1, so x2 is future input. So that's the non-causal system. How about stable? That's very obvious because y only contains the copy of x. If x is bounded, y of course is also bounded. So again, we choose the shortcut here. We put input equals constant. Of course, if xn is a constant, you squeeze the xn over the time index, that's still bounded. It's also constant. So the absolute value of yn is also bounded. So that's called a stable system. How about the memoryless? Again, that's the not memoryless system. That's the memory system. Why? Again, because you have time squeezing. The time squeeze means the input and output timeline are not aligned. So you must have some memory to remember what happens between the time index difference. You can also think about it this way. Recall that in the previous discussion about the non-causal, right? Because this is the non-causal system, so that means you must have some future input, right? If you have future input, what does it mean? For future input, you need a memory, right? So that's the memory system. If you choose a very special case, let's say n equals 1, you have y1 equals x2. So the current input is y1, the current input is x1, but the current output is x2. Okay, so this must be a memory system.